Hello. This is a video on recurrent neural networks, transformers, and things in between. I'm sorry if you can't read anything on the screen at the moment, and that's because I wanted to put together all the references that I thought would be useful for this exercise in one place. But I promise to zoom in and make things readable as we go along. The motivation for the video is that in the last 6 years, especially in the last 2 years, many hybrid between transformers and recurrent neural networks have been proposed, and I wanted to get an overview of the efforts in this direction. So what are the main issues that these hybrid versions are trying to solve, and what are the different approaches that have been explored? So for that, we can first go through RNNs and then transformers, understand the pros and cons of both, and then ask the questions that have motivated some of the works in the middle. So first, RNNs. So recurrent neural networks, as many of you would know, is a very efficient architecture for processing sequential data. So time series, videos, natural language. Why sequential data? Because for such data, it is reasonable to assume that the constituent units will have causal temporal dependency. So in natural language, for example, what I speak next can be somewhat expected based on what I've spoken so far. Now, you can also process such data with convolutions, especially when convolutions have causal masking in them, because then your convolution network will follow the autoregressive property, that is, you are only using the past inputs to predict further. And for high dimensional data such as images, it can be more efficient to use these autoregressive convolution-based architectures than RNNs to do such processing, because you have very efficient implementations of the former for such data as images. And how you define past can be up to you. So for images, you can say that the images are formed from top left to bottom right. So then the past for any pixel are the pixels to its left and above. And you can refer to the Pixel CNN paper for details. Now RNNs are a different architecture and approach in that they process sequential data sequentially over time. So this means that if you have an input sequence of different tokens, so xt is the input token at time t, you feed this to the RNN. Now RNN also has a hidden state, which is a fixed memory understanding of all that it has seen in the past and that it thinks is useful for the task at hand. So it takes in the inputs at every timestamp, it has its hidden state, it uses both to update its hidden state, to update its understanding based on the new data it has just seen. And then again, this hidden state will be available to it to do similar processing in the next timestamps. What it looks like end to end can be understood from this example. So let's say you aim to do language translation. So you have this English sentence, nice to meet you. You do typical NLP data processing. So you tokenize your sentence, get 4 tokens, convert them to vocabulary indices, and then to embeddings, which means that now you have the feature vector representation for each of the 4 words in your sentence. These embeddings you give to the LSTM or RNN cell. Initially, you can set the hidden state to be randomly initialized or however. And this cell will use this input and the hidden state to update the hidden state with the information from this input. And it will make it available to itself in the next timestamp. So processing in this manner will continue until the end of the sentence. And then you hope that all the useful information required for translation in this sentence has been compressed in the hidden state. So the hidden state from this encoder can now be fed to the decoder. So to the decoder, you give this hidden state and a token which says start the translation, so the start of the sentence token. And the LSTM cell here will output scores for every word in the French vocabulary that when passed through softmax will give you the probabilities or the likelihoods that tell how likely it is for that French word to be the first word in the French translation of whatever information is consolidated in this hidden state. So then you can output that most likely word after doing an argmax over the likelihoods. And you also feed this most likely word back to the LSTM, or you can feed multiple of them if you want to do beam search, for example. You feed it back to the LSTM for processing the next. It also gets its updated hidden state, which is it has updated in a similar manner. So now it again uses what it has just predicted and the updated hidden state to predict the next most likely word in the translated French sentence. And this will continue till the decoder ultimately outputs the end token, which means that the translation is complete. So this is your predicted French translation. During training, you will also have the ground truth French translation. You can compare both and get a loss and use that loss to train your network to give better predictions. Now, because the predictions took place sequentially over time, training will also involve backpropagation in time, which means that you propagate the gradients of the loss with respect to the network parameters sequentially in reverse through the network and time. So essentially, you are training the network to be better at updating its hidden state at every timestamp so that eventually your predictions become better. Now, the issue with the propagation of losses through back in time is that that's not very sustainable, and you have well-known issues like vanishing gradients with it. So in a sense, your LSTM or RNN will have short-term memory. And this brings us to the cons of RNNs, which is that the prediction of the next token cannot use tokens in long past or arbitrarily, and we will see that transformers can in fact refer to the previous tokens directly, not even through the hidden state, in an arbitrary manner. And second, training procedure requires backpropagation in time, and that, because of its well-known problems, essentially gives you short-term memory. The defining characteristic remains that prediction is done sequentially over time, and the past information is passed on to the future through the hidden state bottleneck. And you can argue that this bottleneck is the main incentive or driving force for the individual cells to try and extract the most useful information from the input at any given timestamp and then store and maintain it in memory so that they are good at the task. And if they don't have this bottleneck, then maybe they can be more careless about what they are extracting at any given timestamp, or maybe memorize the whole input sequence. With this, the other pros of RNNs are that since they are essentially this cell, you can feed it input as many times and you can get output from them as many times. So you allow variable input and output sequence lengths, and you're able to support all these use cases. So you can give it a single or multiple inputs and get single or multiple outputs, either concurrently or with a delay. Also, you are making the network learn the causal relation in these input-output sequences in both the directions. You can do it left to right or right to left. You can see bidirectional RNNs for that. Also, an important feature is that all the multiple cells or blocks that you're seeing here, they are actually the same block, just unrolled along the time axis to show you what it would look like for this network to process the inputs as they are sent in across multiple timestamps. But all these blocks are the same blocks, and the weights or the parameters of the network, that is this WX, WH, and B, they are shared across time. So this means that doing inference with RNNs has a constant memory footprint with respect to the number of tokens in the input and output sequence. And this is the biggest computational advantage you have with RNNs, that you have a constant memory requirement that's independent of the input and output sequence lengths. Very quickly, the LSTMs and GRUs are essentially iterations over RNNs. So for example, LSTMs, they try to alleviate the short memory problem of the RNNs by being more selective in what they are storing in the memory. So if you're more selective, maybe you can store the more important information over longer input contexts. They do that using forget and some other gates, and also by maintaining separate hidden, and cell state for short and long-term memory. So this means that now they have more parameters that need to be tuned and inferred over. So they are a little trickier and expensive to train and infer. In this regard, GRUs try to strike a balance between the RNNs and the LSTMs in terms of the expressivity and efficiency trade-off. So this was RNNs in a nutshell. Now we can quickly look at the transformers. So transformers have become synonymous with a stack of attention layers followed by a feed-forward network. And attention, when you read this word in all the papers, for example, that we'll discuss later, it means a specific module or operation, and that is this. So this operation involves typically queries, keys, and values. But more broadly, you can say that attention is the dynamic computation of the importance or relevance of the different tokens for the downstream task. So let's say you have a lot of tokens in your sequence and you want to make prediction for an output sequence. So attention tries to dynamically tell you which of the tokens in the input sequence you should pay most attention to so that you're able to correctly predict and place the maximum weight on the correct output token for prediction. We can directly see what that looks like and how that helps transformers. So this is the typical transformer architecture with an encoder and decoder. Let's say you give it the same input as we saw in the last example, so nice to meet you. You do the NLP data processing, get embeddings. Now you also add the positional encoding, and we'll see in a bit why this is important here. So this embedding, you pass through the attention module. For now, let's just say we get some output, we pass it through feed-forward network, and then get the encoder output, which will hopefully, since it's the encoder output, would have encoded all the necessary information from the input in some format and made it available to the decoder. This format is the key value pair, and we'll see that again later. Now for the decoder, you again give it some inputs, which can be some special token, like we saw earlier, or its own past predictions. Again, you do the same data processing, and then you'll pass the embeddings here to the attention module. This time you have it with masking, because for the decoder, when you're training it, you may want it to have the autoregressive property, so you add the causal masking here. And then from this initial part of the decoder, you're getting something called queries. For now, let's just say that the keys and values from the encoder and the queries from the initial part of the decoder, they go into the attention module. Again, you get some output, you feed it ahead, and you hope that from the output of the softmax, when you do an argmax over all the likelihoods, you'll be able to predict the most likely word that should go next in your translation or anything. So now what happens here? Let's say you had the input, it had n tokens, and f is the dimension of our embedding space. From this input, we will extract the keys and values for each of the tokens in the input. So let's say the input was nice to meet you. Then you will try to extract an information map from this input that you can arrange as keys and values. So what information do we get from nice to meet you? You can get how I felt, and the answer would be nice. What I felt nice about, to meet, and who did I feel nice to meet? You. So the answers to all the questions could be the values. So nice, meet, you. And keys are essentially how I'm able to index these values. So the keys can be feeling, action, object. So these together form the information map or the information dictionary. And now when the decoder wants some information out of this map, it will construct queries that will hopefully align with the key that gives me the information that I'm looking for. So if the decoder wants to know how I'm feeling, it will probably create a query that aligns with the feeling key much more than it aligns with the object, or the action key. And how do you check this alignment? You can do that by computing the inner product, and then you pass them to softmax so that the scores of the inner product, they are all in the range of 0 to 1. And essentially now you will get an importance of the different tokens as represented by the keys for the different queries for my tokens. And once you have this token-token relevance map, you will use that to weight your values so that hopefully the weighted value you get from this block will give you the answer to the query that you asked. So maybe in this case, the answer should be nice or good or happy, because that's how I felt to meet you. Mathematically, it looks like this. So you have the query matrix, K matrix, you do an inner product of them, and the output is an n by n matrix, because again, it's the n tokens with n tokens interaction or relevance map. And you do the softmax, and then you weight your values with it. Now you can do this computation for the entire batch of queries at once, or you can do it per query at a time. So in that case, the Q will be a vector, and you can compute this operation with that time memory trade-off. And this essentially was a single head attention. For multi-head attention, you essentially have the same operation being done multiple times. So that is like from the same input, you're extracting multiple information maps, which are like different perceptions and interpretations of the same data. And then from these multiple information banks, you can ask different questions and put them together in a module. That's your multi-head attention. Very quickly, some remarks. So this expression that you see is essentially, again, a token-token interaction computation, and that's very generic. It's also very powerful and almost a universal approximation. So you can compute anything with this, but this on its own doesn't have any bias built into it. So for example, you do not know, if you just give it the embeddings, you won't know their relative ordering in the input sentence if you just give it the word embeddings. So to inject that information into this operation, you essentially have this position encodings, which are typically Fourier encodings, and then you concatenate them with the word embeddings, and then you pass that as X to this operation. Also, the modules that you see here, the first two attention modules here are the self-attention modules. So in them, the queries are the same as keys. So you can think of them as just understanding the token-token interaction within the same input, where you're seeing how does the inputs tokens in the same sentence, how do they relate to each other. So you can think of them as more of a self-correlation, and this as more of cross-correlation, where you're doing this correlation between the query tokens and the key tokens to weight the values. With this, we can quickly list the pros and cons of transformers, which is of course first that the prediction of all output tokens can refer to any input token with short and direct paths. And also in these attention blocks, you typically have multiple layers of attentions stack on top of each other. And because you allow token-token interaction, even though the token can be very long, far in the past, you can still make it propagate till very high among the stack of the attention layers and make it affect any output token. The con, of course, is that because of this extremely expressive token-token interaction, the space and time complexity scales quadratically with the number of tokens. And that's a very big concern. Another good part about transformers is that you can parallelly train them. What that means is, say if I have an input sentence, it was pitch dark, all lights were off, etc. I can generate multiple input-output training sequences from this one sentence, and I can train the network to do the next word prediction for all of these in parallel. So the network can learn to predict lights after all and off after this in the same batch. And this was Transformers in a nutshell. So now that we understand both the architectures, we can ask the big open questions about both of them. For RNNs, one can say that they are this very efficient architectures to infer over, and you can do them for sequential inference. Why can't they also be trained in parallel? And for transformers, you say they are this extremely powerful and general operation that they employ, which is the attention. What if it just didn't scale quadratically with the context length? Or can the attention module somehow reuse the computations from some previous token-token interactions or from the general token-token interaction it could have learned from the data set, say globally, and then use that somehow? So in the original architectures, the answer to both is no. And that is because of this non-linearity present in their expressions. For RNNs, it's more obvious. So let's say if you unroll the RNN processing step for 2 timestamps, you see that you have this tanh, which means you have to do the inner computation first and compute the hidden state at time t-1, inject it, and then find the hidden state at t. If you didn't have that, then you could essentially compute all the 3 expressions in parallel and accumulate them. For transformers, you have these query and key matrix multiplication and a softmax over it. If you didn't have this softmax, then essentially you had 3 matrix multiplications. And for matrix multiplication being a linear operation, you had the commutative property, which means you could multiply these 2 matrices first and then multiply it with the queries. And these 2 matrix multiplication would give a matrix which was d by m in dimension. So you're essentially removing the dependence on the context length n, and your attention could become linear in terms of n if you could update this product sequentially over time. Now again, linear operations, you can sort of implement them either for the whole sequence or for the whole batch at once, or you can do them sequentially using fixed size memory buffers. So that's shown here. We can also probably quickly see it. Let's see. So if I take 2 matrices and I do their multiplication, I have some result. Then I can assume that, let's say I don't have the last entry in both of them. So I just multiply what I have and I've stored that in a variable. And then when I get the new entries, I can also multiply them and store that in a variable, accumulate them to get the same output as I got when I had all the entries together and I multiplied them together. So that's this example. Okay. So now we have asked the right questions, and now we can start seeing it how the hybrid versions answer these questions. Very quickly, when you're thinking of making these hybrid versions between Transformer and RNNs, you can have the following considerations. That is, you may want the hybrid version to have random memory or token access capabilities like the Transformers, have scale and time efficiency at inference like the RNNs. You can also think about how much computation or information extraction you're doing at a single timestamp versus how much you're doing over multiple time in layers. Because you will see that many of the works that try to, for example, reduce the quadratic memory scaling of the attention module, they try to make it linear. And when you try to make an operation linear, you can say you're taking away its expressivity. But then you can argue that because you have multiple of these weakly linear attention modules, stacked on top of each other. So you have these multiple layers, and you have an easier path for the input segment and tokens to propagate through these layers. Maybe what you're not able to extract in a single step, you'll be able to do over multiple stack of these layers. So you can make that comparison. Then again, when you are comparing these hybrid versions from the RNN point of view, you can see how is the information getting accumulated across time. From the transformers point of view, you can try to see what are the paths taken by the input tokens to influence the output tokens. With that, we can start looking at the papers in somewhat detail. So the first set of papers I wanted to look at were papers that were trying to extend transformers to longer context lengths. So that would be Transformer XL, Longformer, Big Bird. And Longformer Big Bird, for example, try to do this by making the attention sparse. So they say we won't compute the n-squared dense token attention. Let's exploit the locality of reference property in natural language. And it's a reasonable assumption to make that for any token, the most important information for that token will be in its neighboring tokens. So, and you also have transformational grammar models that support this assumption that you can make for any coherent language, sentence, and so on. So that is being shown by these blue cells, where you can see that every token is allowed to refer to and access its neighboring tokens within a local window. Then you have some tokens which are of global importance. So they could be the special meaning tokens like the start sentence, or they could be something that you tell the network that these are special tokens for your task. So that can be a way of injecting the knowledge bias into this otherwise very general attention module. These global tokens can also be used as a two-hop path between any token in one segment to any token in another segment, because any token in a segment can refer or access these global tokens, and then the global tokens of one segment can connect to the global tokens of another segment, and from there you can have access to the others. And the third type of attention that Big Bird proposed on top of the previous two attentions that were also proposed in Longformer was the random attention. So that is shown by these orange cells, wherein you say not all tokens are allowed to access all other tokens, but they are allowed to access a fixed number of random tokens, and they are batched for compute efficiency. And of course, when you have this random sparse attention, then you don't have all the tokens connected to all others, but because again you have a stack of these attention layers, so maybe over the stack you will have the full connectivity between all the tokens anyway. And in the paper they also show this with their proofs on Turing completeness and full connectivity. Another thing to mention is that most of these works, for whatever attention operation that they propose, they provide the CUDA implementation. And Big Bird also, for example, gave details on how for the local window attention, you can do the rolling operation and essentially get these different cells into the standard matrix form. The global ones are already in that form, and the random ones, because you only allow a fixed number of them in any given layer, so then you can stack them up nicely, and this is a good memory layout to feed into your GPUs and CPUs. Then before them, there was this work on Transformer XL. So in Transformer XL, you again have this very long input context, and you will say, let's chunk it up into smaller segments that can fit into the memory. And for the individual segments, you can compute attention however you want, but the defining feature is that the tokens in one segment are able to cross-reference the attention for their neighboring segments. So you have the stop of the gradient between the segments, which is that you're not training the attention in the neighboring segment to be a good attention map for this segment. But for whatever attention has been computed by the segment for its own purpose, the neighboring segments will be allowed to refer to it. And the advantage with it, you can already see that even though this input token cannot directly influence this output token, they are in different segments, you still find it in the field of view of this output token with this cross-referencing. So these were, for example, 3 works that were, again, trying to extend transformer capabilities to longer context lengths. Then we have some works which said we are focusing on the same single segment, and we will try to make the attention operation more memory efficient. So in that, the first one, say Reformer, said we will not compute the attention for all the keys and query tokens. We will first divide these keys and query tokens using some hash function into buckets, and then we will compute the attention for the keys and query tokens which fall in the same bucket. Now, with any hash function, you get the possibility that a lot of them can fall into the same bucket, which can defeat the purpose of hashing. So then you chunk them up into roughly equal sizes, and then because genuinely relevant keys and queries can fall into separate buckets after chunking, you allow the cross attention between the neighboring chunks. So Reformer uses locality sensitive hashing for that, and again this is a efficient way of constructing this sparse attention. They also use reversible residual layers so that you don't have to store the outputs for all the attention layers to be able to do back propagation later. Because the layers used are reversible, you can just compute those inputs on the fly during back propagation as needed. Then Linformer, for example, again tries to do the self-attention computation with linear complexity. And for that, they say, and they also try to empirically show, that attention matrix is a low rank matrix. So it's reasonable to first project it to the lower dimensional space. They use their E matrix for that. And now you have an attention which has been computed using these low dimensional projections, so a low rank attention matrix. And then you can deploy the Jensen-Lindenstrass lemma to get a probability bound on how this low rank attention will vary from the original dense attention. What is the probability that this difference will go beyond an epsilon, and you can, for example, get a high probability bound that this will not exceed whatever tolerance you set here. Then you had the work called Performer, which said, let's look at the softmax operation in the attention as a kernel function. So when you look at it as a kernel function, you can try to find mappings that project the operands to a higher dimensional space where their inner product directly gives you kernel function value. And they use random feature mapping to do this mapping to the higher dimensional space, optionally the orthogonal random feature mapping. What is great about their proposal is that depending on how many random feature maps you are using, you can get this inner product to be arbitrarily close to the softmax kernel, and it's also an unbiased approximator in the limit. Okay, so these were 3 works that tried to make the attention an approximate version of the original dense attention. As a result, make it more memory efficient. And when you're doing such experiments for memory efficiency, the kind of experiments that you want to show and that they do can be the inference time versus the input context length or the sequence length. So for the standard transformer, for example, you can see that the inference time varies linearly with the context length, and that's because the y-axis here is the log axis, so log 2 axis. So actually your inference time is varying quadratically with the input context length. And now if you have made your attention linear in terms of the context length, then you will stay constant along the y-axis. So along with the efficiency overview of your proposal, you also want to compare the language prowess or the correctness or the expressivity of your proposal to see that that has not taken a hit in lieu of this efficiency gains. So that you can do by showing metrics such as perplexity, blue, and rouge. And that a lot of these papers do. Okay, so now these two weren't really a hybrid version. Now we start coming to that. So for example, this paper on fast autoregressive transformers with linear attention, they also did something similar to performer, where they said that attention, you can think of it as the softmax in this, you can think of it as a similarity function between the query and keys. And then you can use kernel feature maps to map these queries and keys to a higher dimensional space where the inner product directly gives you that similarity value, function value. So again, you have these mappings and you're projecting them to a different space, and instead of writing the similarity function in attention, you can now replace that with their inner product. So now this involves all the linear operations. So with the commutative property, you can first compute this and then these. The benefit again, as we discussed a little while ago, is that this is going to be lower dimensional than doing this product. And now transformers are autoregressive, or transformers are RNNs, because this you can compute sequentially using a fixed size memory buffer, as also we saw a little while ago. So again, this they denote with S, and this computation for the denominator normalization you denote with Z, and essentially you can compute it for a previous timestamp, and then when in the new timestamp with the new data, you can update it with a similar operation. So this is very reminiscent of RNNs, where you have something carried forward from the previous timestamp, updated with the new information, and then that together updated in the same block. Great, so now we are looking at transformers as RNNs. Now there were some works which said we're not going to try to create approximations of the original standard attention. Let's propose a different attention module. And the motivation for that is, so the standard attention module is the fully dynamic token-token interaction. Just from the data, you can also learn some global position biases and some global token dependencies. So if you learn that and use just that for doing your value weightage, that may be too restrictive. So let's go somewhere intermediate, where you have the global position biases and token dependencies learned from the dataset. And when you get an input token, you use that to only locally modulate around that global static position biases. So in the work synthesizers, for example, each token decides which other tokens it wants the information from based on what it is. So let's say if the input token, you compute its key and you find that you are a pronoun, then it is reasonable, and you could have learned it from the data set, that it is important for you to know which noun you refer to. And in the data set, largely nouns come in the beginning of the sentence. So as a pronoun, you can form the position bias that you should always look at the beginning of the sentence. Or if you are a verb, then you know that in a few tokens from now, you will be told what you are operating on, and maybe a few tokens before, it would have been mentioned that who is performing this action. So for actions or verbs, that can be the position biases, to look a few tokens ahead for the object and a few tokens before for the person. Now again, once you decide this based on the token you are, you can do the dot product attention. And in synthesizers, they also find that random dot product attention also works fairly well. Okay. Now the attention-free transformer also uses this idea wherein they are learning pairwise position biases. So that's an n by n matrix for the n context length. And again, you only additively modulate it based on the token and its key. And then instead of the dot product, you do the element-wide multiplication with the values and with the queries. The only issue with this can be that you are learning a weight matrix or the position bias matrix, which is tied to the context length. So then you have this work on receptance weighted key value, RWKV, which makes the AFT proposal more efficient and extendable to arbitrary token lengths by not learning that W matrix, but learning a W vector. So that W vector has the same dimensionality as the dimensionality of our keys. So every dimension of that W vector tries to learn how much importance that dimension in the keys pays to the past. So let's say if certain key dimensions pay a lot of attention to the past, then the W vector will be such that the attention stays around that token for longer distances and for longer number of tokens, and it doesn't decay too quickly as you move away from it. And again, so once you have this W vector and you have input of any context length and you want to find out for any token T, how much importance should I give to any other token, which is some indexes away from it. You can essentially weight your W vector with the relative distance between that token and the token at which you want to find how much attention to give. So you can do this multiplication of the general position bias and the relative distance between the two tokens, and that will give you this WT T dash, and essentially it's the elements of this W matrix that now you can compute for any context length. So again, in short, RWKV decays its attention on past tokens such that they are exponentially modulated by the global past importance as encoded in the W vector and the current token dependent K. So you also modulate it similarly based on the K value. So very quickly, this is what the modules look like. So you have the input, and now you're extracting only the key and value from it. So you are not extracting queries. So this key and value you give to the WKV block, where you already have the global position bias vector learned. And you will use that with the relative distance between the two tokens and the key of that token to modulate how much attention to give, and you multiply it with its value, and then it's done in a weighted average way for multiple tokens. So you have that for 1 and t minus 1. You interestingly also have it for t, which is that timestamp. So u is another vector which is also learned. So you compute this attention like this now, and again then you pass it on. You also have the concept of receptance, which I think acts as a gate for how much of this attention you are allowed to pass forward. But I have limited understanding of it. Okay, and some very interesting experiments that they show in this paper are, for example, understanding the information propagation path, which we briefly mentioned in the considerations. So for example, you can try to see how the input tokens are propagated along the layers, and then how much they affect the probability of the prediction of a certain output word, which can be the next word in this sequence. So here, for example, you can see that the token Eiffel is already propagated through all the layers. And once it is propagated through all the layers, then perturbation in the layers after this token has been propagated doesn't affect the output probability of Paris too much. So that indicates how important certain tokens are for the prediction of certain words and whether you have that propagation of that important word through the layers or not. Then again, you can see, because now you're computing this W vector, you can see how the different dimensions of this W vector, how much importance they give to the past, and how that importance decays for all the different layers. Okay, so these were works which proposed attention variants. Now we can finally look at a few works which combine transformers and RNNs in, I think, more of a compositional manner. So by compositional, I mean, for example, in the work of recurrent memory transformers, RMT, you essentially have the transformers as the building blocks within an RNN. So you have the memory that is being shared across time to the same transformer basic unit. And then you have the inputs. So the transformers can do the nuanced computation on this input and store things in the memory and make it available to itself for the next timestamp. And this is very reminiscent of RNNs. Then you also have this work by Perceiver. I think the most important contribution of their work was to show that inputs should be viewed as just a byte array, and you can essentially look at them in a domain or agnostic manner. So here you have the latent array, and you use that to formulate the queries, which is essentially asking what information do you want to get from your input for the task. And then when you get the input, you can extract key value information map from it, do the cross attention, and then you pass this information on. Then you can do a self attention again, and that will help you reformulate your queries to know what more information you want from the input now. And then again, you feed the input back to this network for the next timestamp. Again, the information that you're extracting from the input can be different, and you do the cross attention again. Optionally, the weights of these attention matrices, both cross and self, they can be shared between the different repeats. And that's very reminiscent of RNNs, where you have the input being fed to the network at different timestamps, and you have something which is being shared across these timestamps and passed on along these timestamps. Okay, and then finally, the last work that I had put on the list was this Infty-Former or the Infinity Memory Transformer, which have an interesting idea where they are trying to make use of continuous attention. So for that, what they do is that when you get the input, it's of course in the discrete form, but you can fit several basis functions to it. So with that, you do two things. One, you reduce the dimensionality of your input to be a constant dimensionality, because now it's dependent on the number of basis functions you use to model the input. And you can represent them, the input, with the coefficients corresponding to that basis functions. And second, you have found the continuous time approximation for this input. So of course there can be loss of precision here, but at least now you have a continuous time representation of your input, and therefore you can sample from this representation with different frequencies. So if I want a lot of information, fine-grained information about the input, then I can sample very finely. If I just want an overview, I can sample coarsely. And essentially they use this to extract, I think, attentions of multiple resolutions. So you of course have the self-attention, but you not just give it the input, you also give it the short-term memory. And based on the sampling of the inputs and the means or the distribution you fit on it, you get also the long-term memory. And then when you want to update these memories, you can, for example, contract the old memory by sampling coarsely over it, and then you can concatenate it with the new memory, which you have sampled, say, at a fixed rate or based on some heuristics that can again be attention based. So they explain all these heuristics and the short-term, long-term memory, sticky memory in their work, and I found it very interesting. But this was only a high-level overview of a lot of these works. Basically, I just wanted to put them all in a line so I can get the general sense of what is being tried to do here, what all you can try. There's quite some variety here, so it's a very good learning exercise. And this also helps me to put these in my long-term memory. I hope this was useful for you also. So you essentially try to either find linear versions of the attentions, or you try to find reasonings for creating sparser versions of the attentions, maybe based on random attentions or the global tokens or locality argument, or by projecting them to a lower dimensional space using LSH hashing, or by making use of the kernel trick. So you do all these things to make them more memory efficient. And ultimately, then you have works that linearize the attention operation to an extent where you can try to process them sequentially using fixed memory buffers, and that's the perfect intersection of transformers and RNNs. And again, you can have multiple versions of attentions which can be equally good, but we don't yet know. And of course, then we saw some interesting ways of how you can couple these two units together in an architecture. So this was all, and I can definitely be incorrect in my understanding of some of the works that have been presented. So please refer to the original research papers. Also, I have spoken so little of each that I can't do justice to their entire contributions. So again, please read the research papers. And also you can refer to the amazing paper explainer videos by Yannick Kilcher, which I referred for all the works that I tried to explain and for understanding them myself in the first place. So with that, thank you.